Today I'm going to present my paper with the title Truth Discovery on Carousel Sensing of Correlated Entities. This is a joint work with my students and colleagues, Tracy Meng, Wenjun Jiang, Yaliang Li, Jing Gao, Hu Ding, and Yuncheng. Today, we are living in a sensor-rich world. As you can see in this figure, so all kinds of mobile devices, such as the smartphone, the smartwatch, and the smart glass, they can provide us with rich information regarding the surrounding physical world. And moreover, the human themselves are actually the most pervasive sensor in this world, because the human body, is actually a complicated sensing system equipped with powerful sensors, such as the eyes, ears, nose, and the tongue. So all of these human-carried sensors, including not only the mobile sensors, but also the human body sensors, have given rise to a newly emerged sensing paradigm, which is the crowd sensing. In crowd sensing applications, the collection of the sensor data is outsourced to a large crowd of the participants. And each of the participants can report what he learned about the physical and social world through, for example, social media and many other crowdsourcing platforms. And the crowd sensing potentially can benefit a wide spectrum of the applications, such as the cloud wisdom, localization, smart transportation, urban computing, healthcare, and environmental monitoring. However, so currently, the crowd sensing applications are confronted with a major challenge. That is, individual sensors are not reliable. Their sensor data may not be able to truthfully represent the physical world. The problem is caused not only by the quality of the hardware, but also the ways in which people use the hardware. Because we know people in nature are not reliable. They tend to make mistakes. They may have an incomplete view of the observed object. They may be affected by the environmental noise. They may be located far away from the observed entity. They may fail to properly calibrate the sensor. And people in nature are selfish, and sometimes they are even malicious. So they may even have the intent to deceive. So how to address this sensor reliability problem? One common approach is to integrate the observations from multiple sensors that observe the same set of entities, because this can cancel out the errors of individual sensors and can help us find the true value. And this problem of finding the true value about the entities is also known as the truth discovery problem. Let me first give you a very simple example of truth discovery in a typical crowd sensing scenario. Suppose in this case, 3 crowd users detect an entity or object. And suppose in this case, this entity is a bird. And these crowd users want to identify whether the observed bird is a sparrow or a crow. And each of the crowd users locally make their decision. And suppose the first user believes that the observed bird is a crow, while the other users thinks the bird is a sparrow. So there is a conflict in the observations of the users. And in this case, actually, the sensor data reported by the crowd users are actually their decisions. So the sensor data are categorical data. And actually, so in many other crowd sensing applications, the sensor data could also be continuous data. For example, considering the task of air quality sensing, and suppose we want to monitor the PM 2.5 value of a particular city. And in this case, also, the 3 users provide their own readings of the air quality. However, their data still conflicting with each other. So the goal of the truth discovery approaches is to resolve the conflicts among the cloud users, is to discover trustworthy information, which is called the truth, from the conflicting data provided by multiple sensors on the same set of the entities. However, a challenge here is that when aggregating the observations from multiple sensors, we should take into consideration the reliability of the sensors. And some sensors may be able to provide reliable information, some other sensors may not. For example, so if a camera or microphone sensor is located close to the observed bird, so probably it can provide the data with high quality. So for this reason, the straightforward aggregation method, such as the majority voting or the averaging, so may not be able to provide accurate result because they treat all the sensors equally and fail to capture the variance in the reliability of different sensors. However, the challenge here is that the reliability information of the sensors are usually unknown before the object is observed. We can imagine that before a bird appears, we don't know which sensor is located close to the bird and which sensor is far away from the bird. So we will have to infer the reliability information from the observations provided by the sensors. And recently, the problem of truth discovery has drawn significant attention, and the existing truth discovery methods aim to infer both truth and the sensor reliability at the same time from the sensor data reported by the cloud users. And here, the principles followed by the existing truth discovery approaches as follows. First, a sensor is reliable if it provides many pieces of true information. And second, a piece of information is likely to be true if it is provided by many reliable sensors. However, there's still a problem with the existing truth discovery approaches. Because if we only rely on the observation provided by the users, there may be some problem. Let's take a look at another example. So still these three users. And in this case, we suppose they collectively observe 10 different entities. And as we can see in this figure, so not every entity is covered by all the sensors. For example, this entity 8, it is covered by only one user. So in this case, we don't have enough information to achieve accurate estimation of the true value. So how to address this problem? The intuition here is that if we can make use some additional information besides the user observations, we may be able to improve the estimation accuracy. And one possibility of the additional information is the correlation among the entities. And actually, so the correlation exists in many cloud sensing applications. The most representative correlation are the temporal and the spatial correlation. And for example, so in the task of the traffic monitoring, the neighboring road segments may share the same road condition, traffic condition. If a road segment is congested, probably the neighboring road segment also congested. And also, the neighboring cities may share the same weather condition, and the neighboring gas station may share the similar gas price. So let's get back to this example. So here, suppose the correlation exists among the entities. And in this case, the entity E8 is correlated with entity E4. And because E4 is covered by all the users, so probably the estimation of the true value regarding E4 is relatively accurate. And if we can make use of the correlation information, and in particular, if we can propagate the relatively accurate estimation of E4 to E8, so we can improve the estimation of the true value regarding E8. So this is the basic idea of this paper. So in this paper, we aim to incorporate the correlation information in the true discovery process. The input of the proposed approach is first, the observation reported by the crowd users, and second, the correlation information among the entities. And our proposed true discovery approach can output both the truth of each entity and the reliability of each cloud user. And actually, so the correlation among the entities, have been studied. So in my previous work published in RTSS 2014 and IPS in 2015. However, in these two papers, we studied the correlation for the binary sensor data. And in this paper, so we want to study the correlation, for more general heterogeneous data types, especially for the continuous data. We formulated this problem mathematically into an optimization problem. And in this optimization problem, we define two different sets of the variables. First, we associate each of the user with a sensor weight variable. And this variable represents the reliability degree of the information provided by this sensor. The second set of the variable, we associate each entity with also a variable, the truth variable, which represents the true value of this entity. As you can see, the first term of the objective function actually, it is the weighted summation of the distance between the observation of the user and the estimated truth. And intuitively, if a user's observation is close to the truth, we should assign higher weight to this user. And in the second term of the objective function, we define a similarity function, which represents the similarity between the correlated entities. We can use, for example, the Gaussian kernel function of the Euclidean distance between the neighbor entities as the similarity function. And as you can see in the figure, the second term of the objective function is actually a regularization term. It ensures that if two neighbor entities are correlated with each other, so their observations should also be close to each other. And we also have a constraint function. It is used to prevent the weight of the user from going to infinity. So unfortunately, this optimization problem is not a convex problem, so it's difficult for us to find a unique global optimal solution. So because in this optimization problem, there are two different sets of the variables, so naturally, we try to use the block calling descent method to iteratively solve for the two sets of the variables, the sensor rate and the truth. And in the first step, we first fix the value of the truth variables, and we solve the optimization problem only with respect to the sensor rate variable. And this gave us a closed-form solution of the sensor rate. And in the second step, similarly, we fix the values of the sensor rate, and we solve the optimization problem with respect to the truth. And we have another equation. And we repeat these two steps until convergence. However, so this is not the case because, as we can see in the second step, in the equation for the the choose variable. So on the right-hand side of this equation, so there are still some variables, which are the choose values of the entities that are correlated with this entity. They are also variables, so this is not a closed form solution for the choose. So how to address this problem? We propose to partition the entities into disjoint independent sets. And still, we use the block coordinate descent method to solve this problem. And in this case, we have more sets, we have more blocks of the variables. We still have one block of the sensor weight variables. But here, so for each of the independent set, we have a separate block of the choose variables. And in the first step, we still fix all the choose variables, and we solve the optimization problem with respect to the sensor weight. And we still use this formula. And however, in the next step, we update the choose of only one independent set of the choose of the entities, and fix the variable, the choose variables of the other independent set, as well as the sensor rate. As you can see here, so because here, Ni actually denotes the set of the entities that are correlated with the entity Ei. So in this case, because in the independent set of Ei, so there's no entities that are correlated with it. So actually, the choose variables here so are all fixed as constants at this moment. So actually, this equation becomes a closed form solution for the choose variable. So the next problem we need to solve is the construction of the disjoint independent set. And this is actually equivalent to the graph coloring problem. The problem of graph coloring is to actually assign different colors to the vertices of a graph so that the neighboring vertices do not have the same color. So for general graph, so we can use the deserter algorithm, which is widely used heuristic method of finding the minimum number of colors for a given general graph. However, for some spatial correlations, such as the spatial and the temporal correlation, so we actually can have a much simpler ways to construct a disjoint independent set. Let's first look at the temporal correlation. We first divide the time into slots with equal duration. And here we assume that the entities of the current time slot are correlated only with the entities in the last and the next time slots. So we can construct a very simple correlation graph like this. And we can easily partition this correlation graph into two disjoint independent sets. As for the spatial correlation, we can first divide the map into grids, as you can see in the figure. And here, we assume that the entity in a grid is correlated only with the entities in its neighboring grids. So we can construct a correlation graph like this. And we can easily partition this correlation graph into 4 different disjoint independent sets. So this is pretty simple. So let's move to the evaluation part. So I'd like to first introduce the baseline we used. Because in our evaluation, so all the cross-sensing applications are generating actually continuous data. So here we only include the baseline method that can deal with continuous data. We first include 2 very straightforward methods, which is the mean and the median. And we also include 3 existing truth discovery methods that can deal with continuous data. They are GTM, CRH, and CATD. And next, I'd like to introduce the metric we use to evaluate the performance. The first metric we use is called mean absolute distance, MAD. It can measure the overall absolute distance between each method output and the ground truth, which is computed by averaging the absolute distance over all the entities. And the second metric we use is the root mean square error, RMSE. It is computed by taking the root of the mean square difference between each method output and the ground truth. The first experiment is conducted on an air quality sensing system. And in this task, our goal is to monitor the particulate matter with a diameter less than 2.5 micron, which is known as PM2.5. And actually, so in this experiment, we recruit 14 participants, and each of them is equipped with mini AQM. And as you can see in this figure, so mini AQM actually is portable and inexpensive air quality sensor, which is developed by a Chinese company. And it can forward the readings of the sensor data to the smartphone carried by the mobile user. And in our study, the ground truth is collected with thermal. As you can see, thermal is actually a very powerful and accurate air quality sensor, but it is very expensive, and as you can see, it is not portable. So we conduct the PM2.5 sensing in 4 different areas in the Tsinghua University. As you can see in the figure, so in each area, so we measure the air quality of several locations. And here, the sensory readings of the locations within the same area are actually correlated with each other. So we first studied the estimation accuracy of the proposed TD-CORR method and the baseline schemes. And these two figures actually shows the performance accuracy of all the schemes in terms of not only MAD but also RMSE. So as we can see in the figure, the proposed method can outperform the baseline schemes, especially when the coverage rate of the sensors are low. And here, the coverage rate is actually the percentage of the entities covered by each cloud sensor. And this is because, like I said in the previous slides, so when the coverage rate is low, so we don't have enough information to achieve the accurate estimation. However, the proposed method take advantage of the correlation information, so it can achieve a better estimation compared to the baseline scheme. Our second experiment is conducted on the application of gas price inference. And in this application, we solicit the gas price reports from cloud users and aggregate their answers to get correct gas prices. And the prices of more than 2,000 gas stations from 48 cities of the United States are collected. And actually, so the ground truth gas prices are collected from the website Gas Party. And actually, we generate the cloud users by adding Gaussian noise to the ground truth. And we first, study the estimation accuracy, of all the schemes, and still, the proposed method can outperform all the baseline schemes. And we also studied the correlation of the 6 schemes. Here, so we measure the similarity between neighboring entities, and if the similarity score is above a predefined threshold, we say that these entities are correlated with each other. And as you can see in this figure, so the proposed TD-CORI scheme can achieve much better estimation of the correlation, so compared to the baseline schemes. And the last experiment is conducted on the Visor condition estimation. In this case, we collect and aggregate Visor condition reported by the called sensors. And here, the data are collected from different weather forecast platforms. And in this experiment, the temperature of 147 locations in New York City are collected. Still, first, we measure the accuracy of the schemes, and the proposed method can outperform all the baselines. And we also studied estimated sensor reliability degree. These two figures shows the ground truth reliability, as well as the reliability estimated by all the schemes. As we can see, the proposed TD-CORI method can achieve a much better estimation accuracy of the reliability compared to the baseline scheme. This is because the proposed method, because it makes use of the additional correlation information, it can achieve better estimation of the truth. And because the weight is derived based on the truth, so it can achieve better estimation of the sensor weight. And in actually many cross-sensing applications, so there are a very large amount of participants, and these participants can generate a large amount of observations. So in order to deal with this large-scale data, so we implement the proposed method using MapReduce framework. So finally, let me conclude this paper. In this paper, we formulated the truth discovery, the problem of truth discovery on correlated entities as an optimization problem. And then we propose method of partitioning variables into disjoint independent set, and propose a block coordinate design method to solve the problem. And then we also propose a MapReduce-based framework and implement the proposed algorithm on the Hadoop cluster. And the proposed framework bears superior generalizability and flexibility, and suitable for a broad spectrum of application domains. Okay, so this is the end of my talk. So thanks for your attention. So I'd like to take questions.